Now this G, this gravitational constant, has a certain value that you have to measure from an experiment. And it has this value about a very small value, 10 to the minus 11, about 10 to the minus 10, with the proper units to make the units come out. We've got kilograms and mass, meters, and the distance. So you need these units to make things come out with a force in what is used in physics, newtons. Now, Kepler's laws were wonderful. Let's see, let's put it back up here. But when Newton's laws were used to study Kepler's laws, it turned out certain adjustments had to be made such that instead of the sun at the center, it was the center of mass. Or maybe I should say the
center of mass.
The total mass, or maybe center of mass, total mass of the sun-planet system. So that caused a period, instead of the semi-major axis alone, we had the total mass and solar masses. No, I guess I was confusing these two. It's really it's the center of mass at one, center of mass is at one of these foci, not the sun. Of course, the sun is so big that it might as well be the center of mass. But Jupiter, a little off from that, because it's about 1/100th the size of the sun in terms of mass. Let's see. So there were some adjustments, and that led to certain types of orbiting phenomena like binary stars. So you could predict there's a common focus to binary stars. Both of them have the same focus, the center of mass, and both of them orbit that. Okay, we talked about this one already. When you plug in the values of G and the speed being 2 pi times 1 AU over 1 AU. 2 pi times 1 AU over the time, which is 1 year, and then square it and times 1 AU. Then you get the mass of the sun. Just by knowing the details of the distance and the time of orbit, then you can weigh the sun. Turns out you can do a similar thing to weigh the Earth if you know a pendulum. If you know the period of a pendulum, then you can put that in terms of the acceleration of gravity, which can be related to this Newton's law, and the mass there becomes the mass of the Earth, and you can weigh the Earth a similar way. And in a similar way, if you know the orbits of the Galilean moons, for example, Io or Callisto or Ganymede, whatever. If you know their orbital distances and their speeds, you can measure, you can weigh Jupiter. Okay. Let's see, what else did I not cover here? I think okay, maybe I should say something here. These are Kepler's laws, ellipses, equal areas and equal times. Here are here's something called the eccentricity, the oblongness of the orbit is measured by the eccentricity, and a zero eccentricity would be perfectly circular. The bigger the eccentricity, the more oblong it is. You can see from here, Mercury's relatively oblong, and not that much, but 0.2 instead of 0. Earth is pretty circular, it's less than 1. 1 or 2%, and Venus almost perfectly circular. Mars, though, gets pretty oblong, but it's only near 1/10. And Neptune, very circular. Here you get some eccentricity there. Now comets would be very eccentric, so they might have eccentricities of 10 or 20 or more, things like this. But our planets are pretty circular in orbit. Now, if you have exoplanets, there are a lot of exoplanets, planets going around stars in other solar systems that have high degree of eccentricity. So our solar system looks relatively unique as opposed to the Copernican principle. So it seems to violate the Copernican principle. We're a little different than most of what we see, but I think that's just due to the fact what we can see is the biggest stuff, and we can see the most extreme stuff. That's what we can see the most easily. It may turn out to be very much, statistically, solar systems might be more like ours, these highly elliptical kind of orbiting planets in the long run. But look at this p squared over a cubed, that's Kepler's law, almost exactly one. We talked about now I mentioned this before, I think. In order to get 1 AU, that is, Kepler understood the relationships of everything in terms of AU and years. We knew how long a year was. We knew orbits of planets in years. We knew it was in terms of the Earth's 1 AU, but to get 1 AU, people needed some other measure. So parallax was used, this idea where you see things from two different points of view. Mercury looks like it's going, here's Mercury or Venus, one of the inferior planets going across. You could actually see that and see the trajectory from different latitudes. If you have one latitude might look like this, another latitude might look like that. So you have a baseline, and you have some place that's relatively distant. You can get an estimate of how far away Mercury is from the Earth. And you can do that with Venus. And you could do that with actually the outer planets too, using parallax. So eventually, people understood how much 1 AU was roughly, but now we get 1 AU, you weigh 1 AU basically in terms of Venus distance, which we can do through radar. A round trip of a radar beam gives us about 0.3 AU at what we call inferior conjunction. Now Venus, therefore, would be about 0.7 AU. Turns out Mercury is about 0.4, I think, 0.4, 0.3 or 0.4. That's a good one. Okay, that's about it. Let's see. Anything else? Okay. So next time, please hand in homework 2. You may take your homework 1 if you wish to study from. Hand it back next. You'll have a chance to ask questions in the first half hour.
Usually questions that you hear slash chat.
Make sure you take your homework. Give it back.
What type of graphic? No, this guy.